Night pressed down over the launch field in northern Europe. The rocket stood rigid against the darkness, a narrow column of steel bathed in harsh white floodlights. Frost clung to its surface, vapor spilled from its seams in slow, ghostly waves. Around it, technicians stepped back. No speeches, no ceremony, only the ticking certainty of ignition. Then, a violent eruption of flame. The earth shuddered as fire blasted downward, carving a crater of light beneath the tail. For a brief second, the missile seemed frozen in place, straining against gravity. And then it rose, slowly, reluctantly. The roar deepened as it climbed, becoming a streak of fire tearing into the sky. Within moments, it was a shrinking torch against the black horizon. It should have been unstoppable. 30 seconds into flight, the exhaust flickered. The body trembled. A subtle sway became a visible oscillation. The flame bent sideways. The rocket wavered, as if gripped by something unseen. Then, the sky split open. A blinding flash swallowed the missile whole. The detonation cracked across the countryside like artillery. Burning fragments spiraled outward, falling back toward the earth in streaks of orange and white. Germany's most advanced weapon had just destroyed itself. And this was not an isolated failure. It was called the Vergeltungswaffe 2, the weapon of vengeance. To the German public, it was presented as the answer to Allied bombing, a technological miracle that would strike back at London with unstoppable force. Newspapers described it as revolutionary. Radio broadcasts hinted at secret powers. Even its name carried menace. The V-2 was not an aircraft. It was not artillery. It was something entirely new. After launch, it rose nearly 90 kilometers into the upper atmosphere, higher than any machine in history. Its engine burned for just over a minute, pushing it beyond the speed of sound. Then, the engine cut off and the rocket followed a silent, ballistic arc. At the top of its flight, it briefly touched the edge of space. Then it fell, faster and faster. By the time it descended toward its target, it was traveling at more than 3 times the speed of sound. There was no warning whistle, no approaching engine noise, no time to react. The explosion came first. The sound followed after. For civilians in London and Antwerp, the V-2 felt supernatural, destruction arriving from a clear sky without explanation. And that was precisely the point. The rocket was never designed to win battles in the conventional sense. It could not be redirected once launched. It was not precise. It could not strike moving targets or military formations with reliability. It was a weapon of psychological warfare, a message delivered at Mach 3. Adolf Hitler believed advanced technology could reverse Germany's collapsing fortunes. While Allied armies closed in from east and west, the V-2 promised something almost mythic. Scientific leap so dramatic it would restore fear and uncertainty. But behind the spectacle, troubling reports accumulated, rockets exploding moments after liftoff, missiles veering wildly off course, others rising cleanly into the sky, only to vanish in sudden flashes of light before reaching their targets. They were not being intercepted. They were not being shot down. Something inside the rocket was failing, and the engineers did not yet fully understand why. To understand why the V-2 kept destroying itself, you have to step back from the explosions and look at what it actually was. In the early 1930s, rockets were fragile experimental devices. Most climbed only a few hundred meters before tumbling out of control. They were unpredictable, unstable, and widely dismissed as scientific novelties. No nation on Earth had mastered large-scale liquid-fueled propulsion. At Peenemünde, on Germany's Baltic coast, a small group of engineers believed that would change. Among them was Wernher von Braun, young, ambitious, obsessed with the idea of spaceflight. Long before the war turned desperate, his dream had little to do with vengeance weapons. He imagined rockets reaching the upper atmosphere, perhaps one day even the moon. But dreams require funding, and in Nazi Germany, funding came from the military. The V-2 became the world's first operational ballistic missile. It was a machine unlike anything that had ever flown. Its engine burned a mixture of liquid oxygen and 75% ethanol diluted with water. The propellants were pumped into the combustion chamber by a turbopump spinning at thousands of revolutions per minute, powered by steam generated from hydrogen peroxide. Inside that chamber, temperatures rose high enough to melt steel. To survive even a minute of operation required careful cooling. Alcohol circulated through channels around the chamber walls before ignition, absorbing heat to prevent catastrophic failure. Gyroscopes stabilized the rocket during ascent. Graphite vanes extended into the exhaust plume, steering the missile while the engine burned. After cutoff, the rocket followed a precisely calculated ballistic arc, guided by mechanical computers and preset parameters. Everything about it was advanced, everything about it was fragile. The V-2 reached altitudes approaching 90 kilometers. At peak trajectory, it entered near-vacuum conditions before falling back toward Earth at supersonic speed. It was, in effect, the first man-made object to reach the threshold of space. But for all its brilliance, it suffered from one critical mismatch. The physics belonged to the future. The materials belonged to 1944. The rocket's outer skin was thin, rolled steel. Its internal tanks were welded under wartime pressure. Its components were assembled not in pristine laboratories, but in tunnels. After Allied bombing forced relocation, production moved underground to the Mittelwerk facility in the Harz Mountains. Thousands of forced laborers worked in suffocating conditions, carving assembly lines into rock. Ventilation was poor, illness was rampant, food was scarce. Precision manufacturing requires stability, quality control, and time. Germany, by 1944, had none of these in abundance. Deadlines tightened, inspections shortened, skilled technicians were drafted to the front, replacement workers were inexperienced or exhausted. Tiny imperfections began to accumulate. A weld slightly uneven, a seam not perfectly aligned, a microscopic crack invisible to the naked eye. On a conventional artillery shell, such flaws might go unnoticed. Inside a machine that endured violent combustion, extreme vibration, and the stresses of near-space flight, those flaws became fatal. The V-2 was not merely a weapon, it was an experiment conducted at full scale, under wartime urgency, with materials pushed to their absolute limits. And when its engine ignited, forces awakened inside the rocket that would test every joint, every calculation, every compromise. Because once it left the ground, the V-2 entered an environment no engineer of the 1940s had ever fully conquered. The explosions were not random, they were symptoms, and the first signs of trouble began deep within its burning heart. At the center of the V-2 was a chamber no human eye could see during flight. It was small, encased in steel, and hotter than molten lava. When the rocket ignited, liquid oxygen and alcohol surged through feed lines into the combustion chamber. The turbopump, driven by decomposing hydrogen peroxide, forced propellant inward at tremendous pressure. Inside, the mixture detonated in a controlled explosion thousands of times per second. That controlled explosion was supposed to remain stable, but stability, at those temperatures and pressures, is a fragile thing. The V-2's fuel mixture, 75% ethanol diluted with water, was chosen partly to reduce flame temperature and protect the chamber walls. It worked to a point, but under full thrust, the flow of propellant could fluctuate. Tiny variations in pressure, microscopic delays in injection timing, slight inconsistencies in pump speed. Under normal circumstances, these would be negligible. Inside a rocket engine, they became rhythm. A low-frequency oscillation began to form inside the chamber, a pulsing instability engineers later described as chugging. The pressure would spike, then drop, then spike again. Not violently at first, just enough to create a repeating cycle. Each pulse sent a shockwave backward through the feed system. Each pulse shook the engine. The rocket did not simply burn, it vibrated. To observers on the ground, the ascent might look smooth, a bright spear climbing cleanly into the sky. But inside, the structure was enduring rapid, uneven stress. The oscillations traveled through mounting brackets into the fuel tanks, through the tanks into the fuselage, through the fuselage into the guidance platform. The V-2 was long and slender, over 14 meters tall. That shape made it aerodynamically efficient, it also made it vulnerable. When combustion instability aligned with the rocket's natural structural frequency, the effect multiplied. What began as subtle pulsing could grow into violent shaking. Metal fatigue accelerated, weld seams flexed, internal supports strained against forces they were never perfectly designed to absorb. In some flights, the instability remained within tolerable limits. The rocket endured the vibration long enough for engine cutoff. In others, the oscillations intensified. Pressure spikes damaged plumbing, feed lines ruptured, turbopump assemblies destabilized, a surge of fuel or oxygen entered the chamber unevenly. And then, the controlled explosion stopped being controlled. The engine could tear itself apart in an instant, even when the chamber did not rupture. The vibration had already done its damage. Guidance gyroscopes, delicate mechanical instruments, were highly sensitive to shock. Small disturbances could corrupt their calibration. A slight misalignment during powered flight translated into massive deviation over a 200-kilometer arc. From the ground, it appeared mysterious. A rocket that rose normally, then began to wobble. A flame that flickered, a body that twisted. The first visible sign of a battle that had begun deep inside its core. The V-2 was not just fighting gravity, it was fighting its own heartbeat. If combustion instability was the heartbeat of the problem, resonance was its amplifier. The V-2's body was tall, narrow, and almost perfectly cylindrical. 4 fins stabilized its descent. Internal tanks were stacked vertically, one above the other, connected by frames and thin bulkheads. It was elegant. It was efficient. It was also structurally a tuning fork. Every physical object has a natural frequency, a rhythm at which it prefers to vibrate. Strike a tuning fork, and it sings at a specific pitch. Push a bridge at the wrong rhythm, and it begins to sway. Match that rhythm precisely, and even small forces become enormous. As the V-2 accelerated through the lower atmosphere, it encountered a new danger zone, the transonic region. Between subsonic and supersonic flight, air does not flow smoothly. Shockwaves form and collapse. Pressure distributions shift unpredictably across the rocket's skin. Buffeting intensifies. At that moment, roughly 30 to 40 seconds into flight, the engine was still firing at full thrust. Combustion pulses continued to ripple through the structure. Aerodynamic forces added their own irregular stresses. When those forces aligned with the rocket's natural frequency, vibration did not merely continue, it multiplied. The fuselage began to flex along its length. Not dramatically at first, just a subtle, bending motion, almost imperceptible from the ground. Inside, however, the oscillation was magnified. Fuel sloshed unevenly in partially filled tanks. Support brackets experienced alternating compression and tension. The guidance platform, mounted near the center, endured repeated shocks that degraded its accuracy. And once the rocket passed through Mach 1, aerodynamic pressure shifted toward the aft section, increasing structural load where the engine mounts were already under strain. In some launches, this chain reaction remained just below the breaking point. In others, it crossed it. Observers in Britain described strange trajectories, rockets that seemed to corkscrew in the sky, missiles that began straight, then slowly curved into unnatural spirals before vanishing in flashes of light. German engineers initially suspected faulty steering vanes or guidance miscalculations, but post-flight analysis revealed a deeper issue. The rocket itself was bending under certain conditions. The V-2 entered a phenomenon known as longitudinal resonance, the entire structure oscillating along its vertical axis. The engine thrust line shifted slightly with each flex. The guidance system interpreted these movements as deviations and attempted correction. The corrections amplified the motion. A feedback loop formed. The rocket began to chase its own vibration. At that point, structural limits were measured in seconds. Metal fatigue accelerated with terrifying speed. Weld seams that had survived ignition now tore under alternating stress. Internal tanks, already pressurized, deformed against their mounts. Feed lines strained. Sometimes the engine shut down prematurely. Sometimes guidance failed entirely, sending the missile into a widening spiral, and sometimes the vibration reached a violent crescendo. The fuselage would buckle, the propellant tanks would rupture. Liquid oxygen and alcohol, violently mixed under pressure, ignited. Outside the chamber, from the ground, it appeared as a sudden mid-air explosion. Brilliant, instantaneous, final. But what truly destroyed the rocket was not enemy fire, it was mathematics. The V-2 had reached the exact frequency at which its own structure could no longer survive. And even for the rockets that endured the shaking, another threat awaited them higher in the sky, one that no reinforcement could fully eliminate. If a V-2 survived ignition, if it endured combustion instability, if it passed through resonance without tearing itself apart, it was not yet safe. After engine cutoff, the rocket entered a different phase of danger. Now, it was no longer fighting its own machinery. It was fighting physics at the edge of space. At peak altitude, the V-2 arced through near vacuum, silent, coasting, weightless for a brief moment at the top of its ballistic climb. Then, gravity reclaimed it. The descent began gently. Then, it accelerated. As it plunged back toward Earth, the rocket sliced into thicker layers of atmosphere at supersonic speed. Air, unable to move aside quickly enough, compressed violently against the nose and leading surfaces. Compression generated heat, not from friction in the conventional sense, but from the rapid deceleration of air molecules forced together in front of the body. Temperatures rose sharply. The V-2's skin was thin-rolled steel, never designed with modern thermal shielding. It had no ablative coating, no reinforced heat barrier. As the outer shell heated unevenly, it expanded. Internal tanks, still containing residual propellant and pressurized gases, expanded at a different rate. Steel and structure rarely expand in perfect harmony. Small warps formed along the fuselage. A slight distortion in one section altered aerodynamic flow. That change shifted pressure loads. The shift created new stress concentrations along weld seams already weakened by vibration earlier in flight. Engineers had attempted to reinforce certain structural points after early failures. Additional bracing was added, plates were thickened, supports strengthened, but reinforcement came at a cost. Extra weight altered the rocket's center of gravity. The distribution of stress changed subtly during ascent. What strengthened one section sometimes increased strain in another. The rocket became less forgiving. In some descents, heating caused no visible damage. In others, the combined effects of earlier vibration and thermal expansion pushed the structure past its limit. A seam would split, a tank would rupture, superheated gases would escape into confined spaces between bulkheads. The mixture of alcohol vapor and residual oxygen required only a spark. The result was instantaneous. A flash within the fuselage, then total disintegration. From the ground, it appeared as another unexplained airburst, a sudden bloom of fire against the sky. To German commanders, it looked like misfortune. To civilians, it was invisible. The rocket simply never arrived. But to engineers who studied the wreckage patterns, a pattern emerged. The V-2 was not failing because of a single flaw. It was failing because every phase of flight imposed extreme stresses, combustion, resonance, aerodynamic heating, and each phase weakened the rocket for the next. It was a chain of violence, unfolding in stages, invisible until the final flash. And while the rocket was tearing itself apart in the sky, something equally destructive was happening underground, in the tunnels where it was built. The V-2 did not begin on the launch pad. It began underground. After Allied bombing raids struck Peenemünde in 1943, production was moved to the Mittelwerk facility, a vast network of tunnels carved into the Harz Mountains. There, beneath layers of rock, assembly lines stretched through dimly lit corridors heavy with dust and exhaust. The relocation protected the rockets from bombs. It did not protect the people building them. Tens of thousands of forced laborers were transported to the site from across occupied Europe. They worked in suffocating air, under constant surveillance, assembling one of the most advanced machines ever designed. The conditions were brutal. Malnutrition weakened hands meant to weld precision seams. Exhaustion dulled concentration. Illness spread quickly in the damp tunnels. Many workers never emerged alive. The V-2 demanded exact tolerances. Fuel lines had to align perfectly. Tank walls required uniform thickness. Weld seams needed consistency to withstand vibration, pressure, and thermal expansion. But wartime Germany in 1944 no longer possessed the luxury of perfect production. Inspection windows shortened, deadlines tightened. Experienced technicians were replaced by prisoners, forced to learn complex tasks in weeks, sometimes days. Tiny inconsistencies began to multiply across the production line. A weld slightly thinner than specification. A microscopic fissure formed during cooling. A support bracket mounted just millimeters off-center. Each flaw was small. Each flaw alone might have survived ignition. But the V-2 did not experience gentle conditions. It endured violent combustion, structural resonance, and supersonic heating in a single uninterrupted chain. Under those stresses, small flaws became fatal ones. Some historians have documented acts of subtle sabotage inside the tunnels, misaligned components, damaged wiring, deliberate imperfections introduced at great personal risk. In an environment where survival itself was uncertain, even the smallest resistance carried consequences. Whether by sabotage, exhaustion, or simple impossibility, the result was the same. Quality control eroded. The rocket that left Mittelwerk was rarely identical to the one envisioned at Peenemünde. German engineers analyzing failure reports often searched for singular explanations: a faulty pump, an unstable mixture, an aerodynamic miscalculation. But the truth was more systemic. The V-2 required peacetime precision in the final year of total war. It was a machine built for the future, assembled in collapse. By the time it reached the launch platform, the rocket already carried hidden weaknesses inside its frame, invisible, silent, waiting. And when ignition came, the sky did not forgive them. Even when the V-2 survived its own design, even when it endured vibration, heat, and structural strain, its final problem remained unsolved. It was not precise. The rocket's guidance system relied on gyroscopes and preset calculations made before launch. Once the engine ignited, there was no remote correction, no pilot, no adjustment from the ground. The missile followed the mathematics it had been given, nothing more. In theory, that mathematics should have delivered it onto specific targets. In practice, the margin of error was enormous. The V-2's circular error probable, the average distance from its intended aim point, could stretch for kilometers. A factory might be targeted, a rail yard selected, a port identified. But the rocket did not strike with surgical accuracy. It landed where physics allowed. Some impacted open streets, others hit apartment blocks, some fell harmlessly in fields. The destruction was real. Thousands were killed in London, Antwerp, and elsewhere, but it was indiscriminate. The V-2 could not reliably destroy hardened military targets. It could not halt advancing armies. It could not change the outcome of battles unfolding across Europe. By late 1944, Germany's industrial capacity was collapsing. Fuel shortages crippled armored divisions. Allied bombers dominated the skies. The Eastern Front was crumbling, and yet enormous resources continued to flow into the V-2 program. Specialized fuel, precision components, transportation networks, thousands of skilled and unskilled laborers, all devoted to a weapon that delivered fear, but not strategic advantage. It was modern in concept, but primitive in effect. For the civilians beneath its arc, the terror was undeniable. For the war itself, the impact was marginal. The V-2 did not reverse Germany's fortunes. It did not delay defeat. It did something else instead. It proved that humanity had crossed a threshold. A rocket could leave the atmosphere and return with destructive force. And once that threshold was crossed, it could never be uncrossed. By the spring of 1945, the launch sites were falling silent. Allied armies advanced across Germany from both directions. The Reich that had promised vengeance through technology was collapsing under conventional force. But the rockets remained. So did the men who had built them. As American troops moved toward Peenemünde and the Mittelwerk facilities, a race began, not for territory, but for knowledge. Engineers, blueprints, test data, component schematics. The V-2 had failed often. It had consumed resources. It had not altered the war's outcome, but it had accomplished something extraordinary. It had proven that large liquid-fueled rockets could reach the edge of space. American intelligence officers understood what that meant. Under what became known as Operation Paperclip, Key German rocket scientists, including Wernher von Braun, surrendered to U.S. forces. They brought with them technical documentation, test results, and hard-earned lessons written in failure reports. Those failures mattered. The combustion instability that shook the V-2's core became a subject of rigorous American study. Engineers examined pressure oscillations, injector designs, and damping solutions to prevent destructive feedback. Structural resonance was analyzed carefully. Future rockets were designed with altered mass distributions, improved materials, and extensive ground testing to avoid harmonic amplification. Thermal stress during re-entry was no longer an afterthought. It became a central engineering discipline. In the deserts of New Mexico, captured V-2 rockets were reassembled and launched again, not as weapons of vengeance, but as experimental platforms. Each flight produced data. Each data set reduced uncertainty. The rocket that had torn itself apart over Europe was becoming a classroom in the sky, and the knowledge it carried would not remain confined to war. The V-2 did not win the war. It did not force surrender. It did not halt advancing armies. It did not shift the balance of power. By the time hundreds of rockets fell on London and Antwerp, Germany was already collapsing. Cities burned on both sides. Armies moved inexorably forward. The weapon of vengeance delivered explosions, but not salvation. And yet, something irreversible had happened. For the first time in human history, a machine built by human hands had risen beyond the dense lower atmosphere, touched the threshold of space, and returned under its own trajectory. The physics did not disappear with the Reich. In the deserts of the American Southwest, captured V-2 rockets rose again, this time carrying instruments instead of warheads. They measured cosmic radiation. They photographed the curvature of the Earth. They recorded data that would shape a new discipline, astronautics. The engineers who once built weapons refined the same equations for different purposes. Combustion chambers became more stable. Structures grew stronger. Materials improved. Guidance systems evolved from spinning gyroscopes to electronic control. A line can be drawn, not morally, but technically, from the tunnels of Mittelwerk to the launch pads of Cape Canaveral, from a rocket that terrorized cities to a rocket that carried humans to the moon. The Saturn V stood taller, stronger, infinitely more precise, but deep within its design were lessons learned from violent mid-air explosions over Europe, lessons written in shattered fuselages and unstable engines. The V-2 was a failure in strategy. It was a tragedy in production. It was a weapon born of desperation. And yet, in its collapse, it revealed the path forward. Ambition had outrun materials. Vision had outrun stability. Science had outrun ethics. But the knowledge endured. History often remembers the spectacle, the roar of launch, the shock of impact. Less often does it remember the hidden equations, the invisible instabilities, the quiet data extracted from disaster. The V-2 could not save a dying regime, but its failures reshaped the future of flight, and in that final irony, the rocket that fell from the sky became part of the story of how humanity learned to rise beyond it.